we are now going to define interior, exterior and boundary of a subset in a metric space. Let's see this definition 12 to 5. Let x comma d be a metric space, let E be a subset in X and let x naught be a point in X. X naught may or may not be in E. Okay, in general x naught is in X. We say that this point x naught is an interior point of the subset E if there exists a positive real number R such that the ball centered at x naught having radius R is entirely contained inside E. Let us draw a diagram of this. Say this is the Venn diagram of our metric space X, represented by this rectangular region, in which this irregular region is what our subset E is, and inside E we have the point x naught. You already see that automatically a restriction is being put on x naught, that if x naught has to be an interior point of E, it has to lie inside of E. Okay, but what else? Not just that, there should be a ball centered at x naught having some positive radius, of course, which is entirely contained inside of E. If that happens, then we say that x naught is an interior point of E. Now, initially you may think that every point of E is going to be like this. That's not necessary. A point in E may lie here also. I mean, I'm just simply saying, schematically you can think of a point lying at the boundary of E. And I am not using the technical word boundary here, I mean just simply saying what you ordinarily mean by boundary. In this diagram itself, if x naught lies here, then no ball centered at x naught, no matter however small its radius you choose, can ever be entirely contained inside E. So it's not that every point in E will be an interior point of E, but those points that satisfy this condition are interior points of E. Next, we have the definition of an exterior point. Our point x naught is an exterior point of E, or is said to be an exterior point of E, if there exists a positive real number R such that this time the ball centered at x naught having radius R does not even intersect E. Forget about being inside E, it does not even intersect E. So you can see that clearly, that this is the situation if we draw Venn diagram of it. And we say that our point x naught is a boundary point of E if it is neither an interior point of E nor an exterior point of E. What does that mean in terms of those balls? I mean, if you draw a diagram, the situation will look like this. X naught is lying at the boundary of E. I am just simply saying, okay. I mean, in this diagram, you can clearly see that x naught lies at the boundary of E. What it really means is that there is no open ball centered at, open ball means ball centered at x naught having any radius that is entirely contained inside E, because otherwise it would be an interior point, but at the same time there is also no ball centered at x naught which is disjoint with E, because then it would be an exterior, x naught would be an exterior point. None of this is true. Then only we are calling x naught a boundary point. This means that any ball, any possible ball you can imagine whose center is x naught with any radius must not lie entirely in E. That means it has to have points from outside of E, but at the same time must not also be disjoint with E, which means that it also has to have something from within E. So that type of point x naught is called a boundary point of E. Now we are going to consider the sets of these points. So for the set E, we can collect all its interior points and create a set out of them. The set of all interior points of E is called the interior of the set E. and it's denoted by this notation int followed by e within brackets, or you can just simply write int of e, interior of e. Similarly, the set of all exterior points of E is called the exterior of the set E, and it's denoted by ext of E, or like this without using brackets, simply ext followed by E. And finally, the set of all boundary points of E is called the boundary of E, and it's denoted by this notation partial E or del E. So with that definition, next we are going to see this remark. You recall that just now we saw one particular thing in that definition. While we drew that diagram to understand what an interior point is, we immediately noticed that it seems like an interior point needs to be inside the set. But that was just our vague guess from the diagram. Now in this remark we see that actually that is true. Suppose that x0 is an interior point of the set E, then by definition some ball centered at x0 is entirely contained in E. Some ball means for some positive radius. But we already know, we noticed this fact in the previous video itself, that any ball contains its own center within it. So this is a point in this set and this is the subset of E. So obviously x0 will lie in E. So every interior point of E is inside E, and as such the interior of E itself is a subset of E. Next, let us consider a point y in the exterior of E. Then by the definition of exterior, some ball centered at y, say having radius s, is disjoint with E. It does not intersect E. Now just like x0 belongs to this ball, y also belongs to this ball because the center of the ball is y. And this is disjoint with E. So obviously this y cannot be inside E. And these two things immediately tell us that a point in X cannot be simultaneously an interior point and an exterior point of a single set E. That is, the interior of E and its exterior are disjoint. To illustrate these notions, we next have this example 12(2)(7), in which we consider our usual metric space of real numbers, and D is the usual standard metric. And our E is, say, this half open interval closed 1, open 2. So you note this one first. 1.5 is an interior point of E because the ball centered at 1.5 and having radius 0.1 is a positive real number, of course, is entirely contained in E. Luckily, in this case, we can draw this simple diagram, our usual real line, in which you can clearly see what the set E is, this half open interval. In this interval, 1 is there, but 2 is not there. And the point 1.5 sits in the middle. What is this open ball? In fact, this open ball is itself an open interval whose left boundary point you can find by subtracting this 0.1 from 1.5. That means 1.4. It will be here somewhere. And the right boundary point will be 1.5 plus 0.1, 1.6. That is entirely contained in this. So 1.5 is an interior point of E. 3 on the other hand is an exterior point of E. The ball centered at 3 having radius 0.1 similarly would be the appropriate open interval which does not intersect E. There is no common point. It is disjoint with E, and so 3 is an exterior point. However, 1 and 2, these 2 points are boundary points of E. No matter what ball you can think of whose center is, say, 1, can either entirely lie inside E or is disjoint with E. None of these two things will happen, and that is why 1 is a boundary point and so is 2. Note one more thing, and actually the author has chosen this E deliberately like this. The boundary point 1 belongs to E, but the boundary point 2 does not belong to E. So unlike interior points which will always lie inside E and exterior points which will always lie outside E, the case is not that uniform for boundary points. Some points may lie inside E, some points may lie outside E. And based on this, we are in the next video going to see open and closed sets, and sets which are neither open nor closed, sets which are both open as well as closed. All of those things depend on boundary points being or not being inside the set. And in fact, here if you think of it, it won't take really much time to see that the interior of E is actually this open interval 1, 2, in which 1 is of course not there because 1 is not an interior point, it's a boundary point. And the exterior is the union of these two rays. One of them is this open ray -infinity, 1 open, and the other is this open ray 2, infinity. And the boundary is these two elements set 1, 2. And it matches with what we think of these words geometrically: interior, exterior, boundary. Next, we consider this example 8. It is not always that we can draw such nice diagrams which have nice geometry and we can visualize things. Sometimes we just have to simply figure things out from the logic, from the definition. So let X be a non-empty set and we consider this metric space where the set of course is X and the metric is the discrete metric. Say E is any subset of X and X0 is any point in X. Now, if this X0 belongs to E, then what can we say about this X0? Note that the ball centered at X0 having radius 1 is the singleton set X0, and because X0 belongs to E, this is a subset of E. We already know that in a discrete space this is what happens. So X0 is an interior point of E. That means any point of E is an interior point of E. So E is a subset of the interior of E. But we already know that the interior of E is a subset of E. This is always true, and that is why interior of E is equal to E. In a discrete space, no matter what the set is, if you are having the discrete metric, the interior of any subset is itself. On the other hand, if X0 is not in E, then again you can consider this ball centered at X0 having radius 1, which is the singleton set consisting of X0. It is this time disjoint with E, it does not intersect E, and as such X0 in this case is an exterior point of E. Now X0 not coming from E means what? X0 is coming from the complement of E in X. So any point of the complement belongs to the exterior of E. That is, the complement is a subset of the exterior of E. However, we already know from the definition of exterior that the exterior of E is always a subset of X difference E. Where are we getting this from? We are getting this from that remark where we saw that every exterior point of E lies outside E. It is from there that we are getting this, and that is why the exterior of E is X difference E. So in a discrete space, the exterior of every subset is its complement. So what does this mean? What do all these things mean? It means that in a discrete space, say you have a subset E, every point inside E is an interior point, every point outside E is an exterior point, so that leaves no room for boundary points. The boundary is empty. It's not necessary that in every metric space, every subset has to have boundary points. No, that's not necessary, and this is one such case where there is no boundary. No set has any boundary. Besides interior, exterior and boundary points, there is another class of points in a metric space with respect to a subset, that is very important, and we have that in this definition 9. You see closure here, we are coming to that afterwards. So the setup is same. X comma D is a metric space. We have a subset E in X and a point x naught in X. Now we are going to call x naught an adherent point of E, a point that adheres to E. If for every positive real number R, the ball centered at x naught having radius R intersects E. Do not confuse this condition with that similar condition that we have for an exterior point. There is no intersection. Here there is intersection, but at the same time that does not mean that this has to be entirely inside E. It just has to intersect E. It has to have something from E. And we can draw a diagram to show it. In this diagram, again, as usual, the rectangular region represents X, inside of which we have the subset E. And now comes the point. What is the condition here? That every ball centered at x0 must intersect E. So x0 can be like this, because then x0 is inside E. So any ball you can think of whose center is x0 at least has x0. So x0 being a point of E then satisfies this condition, that x0 is already inside the ball and x0 is also in E. But at the same time we can also think of x0 in this situation. Here also all balls centered at x0 must contain something from E. So does this at least vaguely tell you what is the relationship between an adherent point and an interior point and boundary point? It seems like an adherent point is either an interior point or a boundary point, and actually that is true. And note one more thing. What was our definition of exterior point? An exterior point is a point for which there exists at least, okay, I am again saying at least one ball centered at that point which does not intersect E. However, for an adherent point, every ball you can think of whose center is x0 must intersect E. There at least one ball not intersecting E, here every ball has to intersect E. So you should not forget this aspect also. Every at least one. Now before we can see that relation, let's complete the definition. The set of all adherent points of E is called the closure of E, and we denote the closure of E by this notation, E bar. And next, here is the proposition linking those things. Again, let x comma D be a metric space in which E is a subset and x0 is a point. Then you can see these three statements, they are logically equivalent. If any one of them is true, then so are the other two. The first statement is this: x0 belongs to the closure of E. This means that x0 is an adherent point of the set E. The second one is that x0 belongs to the interior of E or x0 belongs to the boundary of E. That means x0 is either an interior point or a boundary point of E. These two are equivalent. The third one is a little different. It involves a sequence and convergence. Actually, this is very useful. You will see why. There exists a sequence xn in E, in the set E, which converges to that point x0 with respect to the metric D, of course, because everything is happening in the metric space x comma D. So if any one of them is true, then the others are also true. So you can see that the equivalence of A and B already tells you that every adherent point is either an interior point or a boundary point. Conversely, every interior point is an adherent point and also every boundary point is an adherent point. And if you express this as a relation between, linking these three sets, it's just this: closure is equal to interior union boundary. And the proof of this is one exercise. So it's not available in the text. So when we solve the exercises, then we will prove that. And let me just end the video here itself. Next week on the same day, we are going to use the notion of boundary points to define open and closed sets. And then we will have the usual properties of open and closed sets. Actually, you already know about them, but we will see what we are going to get. So see you next week with those things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.